So my name is Eugene Dvorkin. I work for WebMD, the biggest site for medical information and news. And also I am organizer of Storm New York City meetup, where we discuss all problems with scalability and real-time processing. So you can send feedback or tweet if you like my session or don't like my session. It's important for your feedback. So today we will be talking about stream processing. What stream processing means. Then we'll talk about Storm architecture, what Storm brings to the table, Storm abstraction, parallelism, how Storm processes messages in real time, and we talk how to set up Storm cluster, and what it means to be fault tolerant. It's especially important for real-time system. Then we talk about TRIDENT, which is high-level abstraction on top of Storm, and then I show what we develop at WebMD with a real-time framework. And then question and answer. So let's talk about stream processing first. Like several months ago, our business people come to engineering and say, we want to process tweets. We want to get tweets in real time, do something with them, and display nicely in a mobile web application. It looks like a trivial task initially, but when you realize what you have to do. So you have to build streaming system that will read tweets and then make it available for web application or for mobile application, right? It's all nice and cool until you realize that there's about 6,000 tweets per second, or 350 per minute. Even if you don't read all of them, this tweet fire hose, if you read only 1%, it's about 3,500 per minute. This is a lot of volume and a lot of velocity coming at you. So how you build system that will support it? How you scale? Definitely you cannot run it on one machine, and especially if you do some complex stuff. So how you scale? You may think, oh, okay, I can use Hadoop. But the problem with Hadoop, it's a batch system. You have to put data, and then you run your job, and maybe in a couple hours you get result. But Twitter, it's all about real time. You tweet, you want to see it maybe a couple seconds later, maybe max like 30 seconds later, but not like a couple hours. So Hadoop like went away out of questions. So how you would do with traditional system? And why you start thinking about it now? So right now, there's exponential rise in real-time information. Twitter, log files, all these devices that emit some signal. People understand if they react, they can get some business value out of it, if they can react in real time. And this complex event processing systems that react on events, they exist before, but they was very expensive actually. But nowadays, you can download something from GitHub, open source software, and commodity hardware make it possible for companies to do real-time stuff very inexpensively. So what's use case? For example, detecting fraud if someone's swiping credit card. That has to be done in real time. Placing advertisement on a website, why somebody reading relevant articles, so you want to put relevant advertisement to get better response, right? Alerts, application failure, machine failure, some device failure, you want to raise alert right away. That's another use case. And even another use case, it's exact transform load. Why wait and run it in batch when you can stream your data from one system to another? For example, at WebMD, what we did, we stream data from MongoDB directly to BI, so they can run their report much faster. Don't wait, right? So here's a basic processing flow for stream application. So you got real-time data, you got your system, and you persist data into database. And then application pick it up at the time they wish, but data already available. And also you have alerts. That you can have real-time alerts that goes into different dashboards. Here how you would build system by yourself. So you may have Twitter, Firehose, you may have queues, you may have workers because you have to distribute among different machines. You may have another queue, and then finally you save it to a database. If you do this type of work yourself, you have to answer the question, how I scale this system? How to deal with failures? What's to do if message somewhere failed message? How I replay it, or should I ignore it at all? So you spent your time doing not business logic, but a lot of infrastructure. And dealing with all that complexity, it's a painful, right, and tedious to code. So that's where Apache Storm project come in, to solve this problem, to give us developers, especially in business environment, a way to scale and create stream applications. If you look at Hadoop, I look at like big imposing elephant in a room. Storm, it's like fast horse. You can do a lot of stuff and very, very efficient. So let's talk about Storm history. Storm was developed by a guy named Nathan Marth back in 2011. And the whole company got acquired by Twitter in the same year. And then Twitter open sourced this project. And in 2013, it's become Apache project. It's important when open source project become part of Apache because it gives it a lot of credibility. And for people who are looking for commercial support, now it's even part of Hortonworks distribution. And it's out of all streaming platforms, that's the most widely adopted and most mature. A lot of companies use that. That's a screenshot I took from Storm Incubator, apache.org. And if you look, you have company like Twitter and Spotify. This company always runs something latest and greatest. You say Spark, they're running Spark in production. You say something, they already does it. But company like WebMD, or Alibaba, like traditional corporations, they're very slow in adopting new technology. Meanwhile, they do with Storm. And also, if you look, it's across different industry, music industry, e-commerce. So it's across different industries and companies, size and different size of companies. So to understand what Storm is about, let's talk about Storm properties. So first, Storm is about stream processing, right? That's the first. Second, it's fast. Cisco running 1.2 million network packet per second using Storm. It's scalable. You just add more hardware, commodity hardware, and you scale your cluster. And Storm fault tolerant. If something fails, Storm will take care of that. So it's a real-time system. Like if your batch job fail, you come in the morning and you fix it and you run your report, it's ready. If real-time system fail, it's not real-time anymore. It defeats the whole purpose. So it has to be fault tolerant. It's also reliable. It's guarantee that message or event, whatever you're receiving, will be processed. It's also run on Java virtual machine. That's why we talk about this at this conference. And it's very important because companies know how to run Java, how to tune garbage collector and so on. And Java, it's like everywhere. So it's important. But interesting thing, you don't have to use Java or Groovy or any JVM languages to run component inside Storm. You can use any language practically. Want to use Python? Go ahead. C#, you name it, almost any language. And it's easy. It's easy to learn, easy to run, and easy to administer. And I show you an example of that. So to understand Storm, we have to understand some abstractions. First is data. Data type. Inside Storm, it's called tuple. Tuple, it's a key-value pair, basically, immutable key-value pair. And for example, like word, hello, count 25, that's a tuple, right? Then you have stream. Stream, it's a sequence of tuple. So it's like streaming those tuples, million maybe per second, whatever. And then you have source of the stream called spout. What spout does, it takes data from external system, from message queues, from weblog, from API, from database, and emit it into Storm. So that's the role of the spout. And then you have Bolt. Bolt is processing unit. That's the guy who does the job, analytics or whatever. For example, it does calculation, call to database, call to external APIs. That's all done in Bolt. And also, Bolt produce a new stream and emit it. And to link all together, we use topology. Topology, it's a network of spout and bolts. So you define your workflow, you define your data workflow as a graph, as a computational model. So in this example, I have one spout and many bolts, but it's it depends on your use case. You may have many spouts and even more bolts. So, and we have to understand another thing, what is task. Task is instance of spout and bolt. Because it's like scalable system, you can say, I want to run 5 instances of this spout on this machine. And I want to run 20 instances of a bolt on another machine, so another 10 machines. So it's a distributed. So task is instance of a spout or bolt. And another concept we have to learn is grouping. How you send data between instances of a bolt. And this actually 2 of them. There's more, but 2 most used. One is shuffle. Shuffle grouping, it says just round robin, just random. So it's get tuple, one bolt get tuple, and randomly send it to the next bolt, right? And there's also field grouping. Field grouping allow you to send data based on the field. For example, you do word count. If you randomly send each word to next bolt, each of them will have count, but incorrect. So you want to group by field and send to next bolt. So that bolt will have total count for that particular key. So just to summarize, we have tuple, stream, spout, which is you have many instances of a spout if you want to, and you have bolt, also many instances running across machines, and topologies that link this whole thing together. So let me show you how easy it is to code. I claim Storm is easy. Let's see. So first you have to do is, of course, get dependencies. The latest version is Storm 0.9 incubating just from central Maven repository. And then you have to build your topology. When you're running Java, the first example is hello world. In Hadoop and all distributed system, it's more about word. It's a word counting example. That's people run first. So how we do that? We get a spout that will emit sentence, right? Something like that. Then we have bolt that will split that sentence into word. So we get many tuples. Actually, we get 6 out of that sentence. Then you have another bolt that will count how many times this particular word happens, right? So, for example, something like that. And then just for demo purposes, I print it out. I create a printer bolt. We just print out final count. Let's say run it and print final count for some time. So let's build it. So first, data source, right? We will be using just array. Code is in Groovy because we want to run production code, not all the ceremony and stuff. So Groovy, very good match with Storm, and there was no any compatibility issue at all. So here's the sentences that we will be emitting. So let's create a spout. First thing, we have to create a spout. When you create a spout, you extend base rich bold class, right? And then you have to say, this spout, which field this spout will emit. So you declare that this spout will emit sentences, right? Then you do some configuration. In this particular case, I don't do anything, but if you need to, like, say, create a resource, like database connection, API, you put all resource allocation here in open method. And then you call override next tuple method, and you emit your words. So basically, you emit new tuple. You create tuple and emit it. So what's happening in this code? It's constantly going over this array and emitting each sentence. Is that OK? That's all, actually, about Spout. We're done. Now we have to write a bolt that will parse this Spout, will parse this tuple. Remember, tuple has, right now, our tuple is sentences. Right? So it's extend base rich bold class. Again, you declare output from that bold, and that will be word, right? And then there's a prepare method, which like life cycle method. What you put, again, resource initialization. If you want to talk to database, you put connection, string initialization, all stuff here, right? And then there's execute method, which get tuple as a parameter. That's the only parameter it's get. And then you extract value. In that case, I extract sentence. You split it, and you emit each word as a tuple. And that's all. Now you go further. You create a next bolt that will do calculations, right? Again, you declare what that bolt will emit. In our case, we will be emitting word and count, right? So again, prepare method. Here I will just use a hash map, and I put word and count into hash map. Again, I'm getting from previous bolt, I'm getting word, right? And I just put it in a map saying, OK, if that key exists, add 1. If not exist, it will be just 1. So in that hash map, I will have the whole count for each word. And then I emit, in this particular case, I am emitting a word and count. So you see declare method, word count, and output, they match. So I declare that I will be emitting word and count, and I do emitting word and count. And my last is printer bolt. Yes? So, parallelize what? Yes, 1 second. This one?
Yeah, the execute method. You're basically incrementing the count and then assigning it to a local map.
Right.
And so how would that be parallelized?
OK, yeah, that's a good question. That's why I talked about, I will repeat that, I talked about field grouping. So each instance will have his own key. So let's say you have that will go to one particular instance. It's never go across. So that instance will have only this count, only count for this particular key. So if you have 100 instances and you have 200 words, each instance will keep only 2. Make sense? OK. And finally, we have printer bolt, which again, here we don't declare anything because that bolt will not emit anything. And then execute method that I put again in a map. And I use cleanup just for demo purposes. When I shut down topology, cleanup method will execute and print out what's left, what we have in a hash map, the whole word count. And finally, we have built all this component, and now we want to link them together. And you do it in topology. So you create a topology builder class, and you set up, you just say which spout you want to use, sentence spout, and you now stitch together bolt that listen to that spout, and then you stitch together next bolt that listen to previous bolt, and so on. And you have also some configuration things. If you want to use, let's say, true, like debug equal to true, and other configuration for the cluster. And here I starting local cluster. What means starting local cluster? You don't have to have any distributing system at all. You can run on your laptop and check your ideas that they're working and test everything before going to distributed mode. And finally, you submit your topology. And that's practically all you have to do to create that simple topology. So let me show you how it runs real quick. So here's my topology. I run as a Groovy script, but if you write in Java, it will be in main method, right? So exactly the same as I showed before, and I just run it. Our word count topology. So what will happen now, Storm will be instantiated on your local machine, create all necessary dependencies, everything, and start executing start listening to your stream. I think I'm running it for 8 seconds or so. Yeah, and here I got counts for 8 seconds. So the idea is, when you start topology, it's run. It's never finish. It's not like a bad job that finish at some time. You run it, it's constantly finish and updating your counter or do whatever you need to be done. So let me kill it. And return back. Okay. So let's talk about parallelism. So for now, we just did simple one machine things. So how you parallelize Storm, how you make that job. So to understand that, let's talk about what's involved in cluster. So you have nodes, it's machine on a server, some terminology, and you have workers. Workers is Java virtual machines that run inside your nodes, right? And also you have executors. Executors, it's practically thread, JVM thread, right? And you have your task, which is bolt and spouts, right? So how you configure parallelism? Let's imagine you have two nodes. You have machine of two clusters, right? In Storm, you can just say config set number of workers. So it will automatically allocate 2 machines and 2 JVM for you, for your topology. Then you can say, there's a parameter called parallelism hint, and you practically saying, I want this word count run in 4th thread. So it will allocate 4th thread and put word count task into these 4 threads across machine automatically. If you don't specify anything, let's say you didn't specify any parameter, by default it will put 1 task into 1 thread, right? But there's also option, you can say number of tasks. If you specify number of task parameter, it will put 2 tasks in 1 thread. You may say, what's the parallelism here? But in some use cases, it's very useful, especially if you have I/O intensive operation. 1 thread can handle and wait and switch and do that stuff. So that's how Storm achieve parallelism. So you see, when you have cluster from you as a programmer, you don't have to do much. That's all it takes. And here's its example. When you're coding, Here's this number parallelism hint. You just say this bolt, I want like run two instances of this bolt. I want this bolt run 2 tasks of those bolt. And the whole thing I want to run on 2 machines, on 2 GVM. If you have a machine of 200, you can put 200 here. Not only machines, you have 200 GVM instances running, and you think you need to really scale. It's up to you how much you can put. So no problem. And also going back, here how you specify shuffle grouping, how you specify how tuples move between instances of bolts. You can say shuffle grouping. In that case, shuffle grouping, again, it's random. But because we don't care the whole sentence, who will parse the whole sentence? But we do care when each word emitted, that word as a key will go to the same instance. So we put field grouping here. So that's how you parallelize practically. Okay. Another property of Storm, it's guarantee message processing. What that means, let's say this in our topology, we emit sentence and then it's go break down and so on, right? So we created like a tree. So it's called tuple tree. So what Storm does, it's check if at any point some failure happen, it will react and replace the whole tuple tree from beginning. It's always replay from beginning. So let's say some tuple fails some down the line, the whole thing will get replayed. That's how it's achieved this message reliability. It's called at least once semantic. So it's guaranteed to process your message at least once. And how you do this? It's not necessary that you have this semantic. It's up to you. Sometimes you maybe don't care. Let's say failure happen very infrequently. You may skip the whole this notion of reliability and just code as I did. So the notion is if 2 or 3 tuples fails out of a couple millions, who cares? But sometimes people do care. And that's, you have to create this reliable API. You have to use a reliable API to tell Storm to track each tuple and replay it from start. How you do it? In your spout, for each tuple, you assign unique ID. Right? Here I just assign a random unique ID. And this also 2 methods, arc and fail. If tuple process successfully, arc method will be executed on a spout. So you can do something or do nothing. If it fails down the line, fail method will be executed on a spout. And here you can put code to send this tuple again, right? On the bolt side, you have to help Storm and tell him that I'm start to track each tuple as it goes process. That's process called anchoring. So you emit not only new value, but you emit original tuple as well. And the same ACK method, if everything's successful, you tell Storm ACK that this portion of processing complete. Storm by default will track each tuple for 30 seconds. If 30 seconds it did not act, it will say it's failed and try to replay it. And if it's failed, you tell Storm I'm failed. So the whole call will go back to Spout and replay it from the scratch, from the start. Okay. So how you test your stuff? How you test bolt and spout and all that things? It's turned out that you can test each component separately, and which more important, this is Storm testing API. So usually people say it's a big data, it's not testable or stuff like that. Not the case with Storm. And there is a very good resource on GitHub, testing API demo. You can see how it works. But we use SPOCK, and it's worked nicely with SPOCK. For you who's not familiar with SPOCK, it's awesome testing tool. And check if there's any session about SPOCK, behavior-driven development. So we're basically saying here, create a tuple parameters. We just specify what we will be emitting. We're just creating a stream. Here's just regular mocking from SPOCK, mocking framework, and then regular stuff, just instantiate our bolt and call prepare method. And here we're creating tuple. You cannot use mock from SPOCK, but there is a testing class from Storm itself that allow you to create test tuple, right? And then you execute your tuple, and you can check using regular SPOCK stuff if ACK method or execute method. So testing API do help a lot. Okay. Any questions so far? Okay. So let's talk about how Storm run on a cluster, what it takes to run cluster. So here's how a physical view on a Storm cluster. You have NIMBUS. NIMBUS is a guy who is responsible for getting your job and distribute it across machines, and also track it. What's fail, what's not, how to reassign task. It's all NIMBUS responsibility, right? Then on each node, you have supervisors. Supervisor is just a guy who receives signal from NIMBUS, get code, and start Java virtual machines, start workers, monitor those workers, reassign if workers fail. That's a supervisor job. Right? And of course, you have a most distributed system. You have Zookeeper that keep state information about nodes and who is running, who failed. So all coordination happen via Apache Zookeeper. So how you package your topology? So let's say you install the Storm cluster. So now what you do? You get your Java application or Groovy application, and you create a big so-called fat jar. You package all dependency together. And Gradle, I use fat jar or shadow jar plugins to package it all together. And then this Storm submitter. It's when you install Storm, you will see a Storm command line. So you just say Storm jar, name of your jar file, and name of your topology. And that will go to NIMBUS. Your code will go to NIMBUS, and then it will be distributed across machines and start executing almost instantly. And as soon as it starts executing, Storm will give you a nice UI. And in this UI, you will see your topology is running. You will see how many tuples emitted, transferred, what's going on. You will see latency. So that's invaluable tool. So when you do performance optimization, you will see how long, let's say, word count takes, right? Is that good or bad? And also it's tell you, for example, capacity. What's capacity? It means, let's say, out of 10 minutes, 9 minutes and 30 seconds, your bolt is busy doing your task. Its capacity will be almost close to 1. So there's no additional stuff this bolt can take on. And it will even flash red for you. So it means it's time to parallelize more. Maybe bring new GVM or bring new machines or increase parallelization settings. Right? OK, let's talk about fault tolerant. Real-time system has to be fault tolerant, right? So what that means? Let's imagine everything works nice and cool. Everybody happy, everything works. Now NIMBUS went down. What's happened? Actually, nothing happens. Because if you remember, responsibility of a NIMBUS, it's to submit new jobs, right? But our existing job continue to run. So nothing happens. You lose ability to submit new stuff, but existing job will be running. Moreover, you run under supervision. You run under Monit or Supervisor D, so maybe in a couple minutes, Monit will restart your NIMBUS process, and everything will be back to normal. So no runtime, no like interruption in service. Let's say the whole node went down. NIMBUS will reassign all these tasks to another node, as simple as that. Now let's say supervisor dies. Also not a big problem because he doesn't do much job. Worker does. Supervisor just monitor if worker alive or not. So if he dead, that's not a problem. And now if worker dies, supervisor will notice that and restart this worker. Either restart this or reassign task. So everything, like monitor it and make available real time. Okay. TRIDENT. How many of you are familiar with Hadoop? Yeah? Oh, a lot of people. It's a good audience. Okay. TRIDENT is high-level abstraction on top of Storm. It's similar to Pig or cascading in Hadoop, right? What it does, it's instead of bolts, well, not instead, you don't write your bolt. Storm will automatically create bolts from you, but you write function, filter, aggregations. And there's a lot of those already exist in TRIDENT, right? And it's also micro-batch processing. It's not sending tuples one by one. It collects them into micro-batches. Also, TRIDENT provides exactly one semantics. If you remember, Storm provides at least one. TRIDENT provides exactly one. What the difference is? For example, you have word count topology. And let's say you count failed at some down the line, right? Your tuple failed. Storm will reprocess it. So you will have the same word counted twice. So you can double, triple. Your count will not be correct. In TRIDENT, that will not happen. It has exactly one semantics. So if it's fail, no worries. It will not overcount. And also, it supports state. It has API to writing to databases, and you can query that back. So here's the most important things. One of the most important, it's a micro batches. So stream process in a small batches. And another things, each batch has a unique ID. And that ID stays the same on each batch if batch has to be replayed. What TRIDENT does, if one tuple in a batch fail, it will replace the whole batch with the same ID. And also, it's ordered batches. And that's how it supports one-over-time semantic. So how it does that internally? Well, the trick is that TRIDENT use is to keep batch ID together with count. So it keeps this additional metadata information. So let's imagine you have batch ID, let's say 100 tuples in it, and count become 101. Now 10 more tuples come with batch ID 2. So count become 210 and batch ID 2. And now let's imagine one tuple in batch ID 2 fail. TRIDENT will reprocess, send again all these 10 tuples in the same batch, batch ID 2. But because TRIDENT keeps that batch ID number, it says, oh, I already processed batch ID 2. I am ignoring you. So it will ignore that. So by keeping that, but in order to do that, Spout has to be able to emit the same tuples inside the same batch, right? So that's how TRIDENT achieves once-at-time semantic. But you don't have to deal with that because TRIDENT API hides this complexity from you, and you don't have to code these particular things. And I show you an example. So for example, return back to our word count topology, right? That we wrote in Storm, pure Storm. Now let's write the same thing in a TRIDENT. So instead of sending random or next element in array, I will be using fixed batch spout, which also comes with Storm, just maybe for testing purposes. And I would say, OK, emit these sentences in batch of 5 and emit it constantly, never ending. Right? Then instead of Storm topology, I create a TRIDENT topology. And I say, OK, here's my stream. I create a stream. And then I specify that stream will have field sentence. I create a new function called split sentence that will emit new field. It's used at Java Fluent API. So you build your topology using Java Fluent API. Then you group by this word. So instead of field grouping, you just say group by, see more high level. And then you say, for example, here I'm doing persistent aggregate. It means saving into local memory aggregates of a count function. So whatever counts happen, I will save it in memory. And you can, after saving, just for demo purposes, you can create a new stream. And then you can use like debug method to see what's going on. Everything else stay pretty much the same. And here you can specify how many batches you want in your system to be running at one particular time. So this is like max spout pending. It's more like not to overload Storm topology. Let's say you don't have enough computing power to read that batches to as they come. You can say, OK, set max spout to 20. It means only 20 batches it will emit. And until some batch get processed, it will not emit a new one. So it's like in a spout, like, put more or less. Right? And the same story, you just submit your topology to local cluster. And if it's, if it's on your local machine. And here's how you write your function. Split sentence function. Instead of split sentence bolt, you write a function. That's all code it takes. You just have a split method here. That's all about functions, how you create. So let me demonstrate that, how that works. Here. OK, here's our fixed batch spout, and exactly the same code as I demonstrate to you. So if I run it, TRIDENT topology. So as you remember, it's constantly emitting stuff. Here it is. So here's our word count. So it's never-ending process, practically. OK. So for how long it's run, we will see that how many different words were emitted. OK. So if we compare Storm to TRIDENT, first it's different computation style. One at time. So TRIDENT it's one at time, and Storm it's one at time. TRIDENT it's batch processing. TRIDENT provide high throughput because Storm don't have to keep track of each individual tuple. It just keep track of the whole batch. And at least one semantic is on both sides, but exactly one semantic it's only in TRIDENT. And plain Storm a little bit simpler, more visible, I would say. Because in TRIDENT, when you submit your TRIDENT topology, you don't know how Storm will create bolt and spout. It's like he does it by itself. It's like a little bit hide from you. But otherwise, they're very similar. So TRIDENT, it is Storm. It's just addition on top of Storm. So let's go back to our challenge, how we use this thing. So as we remember, we need to create a streaming system that will read all these messages from Twitter and make it available for our application. What we do with our application? So our business decided to create this Today on Twitter stuff, and that's like medical related news, and also related for each profession. If you're an oncologist, you see news in oncology. If you're a cardiologist, different, so it's for medical professionals. And also we have a MEDPULSE application, which is very interesting application. That's the only web application I'm using myself from WebMD, because it has feeds from different sources like New York, about health, about very interesting topic, not only to medical professions, right? But in order to do that, we want to enhance tweets. So for example, here's a tweet that has only link to URL. What the business wanted is we have to go to that website based on link, grab lead image, figure out which is lead image, then scale it down so it looks nice on mobile device, and also get title of image. So it's called readability enhancement. That's one things. So also, we want to remove duplicates if somebody retweet or tweets the same article in some period of time and stuff like that. And also, there is tons of business logic, even as simple as if its favorite competitive product, like don't show it, kill that tweet, right? So that's our task. And how we build it? We just create a streaming system based on Storm, and we save data to MongoDB. And then we have built on top of that, we build REST API, and mobile and web application just pick it up at the time when they need it. So the whole thing maybe take like couple milliseconds or second, but user will be able to see it almost in real time. And how you work with Twitter particularly, that's interesting because Twitter has two types of APIs. They provide a so-called REST API, when you just request response, and streaming API. Request response REST API have a severe limitation on usage. Do not call us more than 100 times in like 10 minutes or so. But with streaming API, you just open connection and you listen to tweets. And as they come, you just get them. So it's a very good API actually to use if you work with Twitter. And they return you back huge JSON with status, they call it status, but it's in JSON format with a lot of information about tweet and author and what's not, right? And of course you can use, if you're in a Groovy, you can parse it yourself, but probably not a good idea. This very robust Twitter for J library that takes care of authentication, authorization, and automatically converts that JSON into status object. And also has listener, very good library. So how you create Twitter spout? Okay, you don't. You just go to GitHub and grab one. And not only for Twitter. Well, it's a demo on GitHub for Twitter spout. It's maybe not like super production quality, and they say about that, so you need to do some enhancement. But for many other projects like Kafka, JMS, RabbitMQ, very good quality, production quality Spout exists. And they exist inside a contribution section in a Storm repository. So you just grab whatever your connection you need, and it's open source, and you use it. So saying that, that's what we end up with our topology, right? We have Twitter spout, readability, bolt, image processing. So you build your workflow, right? And save to MongoDB finally. And Storm takes care of scalability and fault tolerance. But there's one problem. What if there is a burst in traffic? What's like Ebola outbreak, and suddenly your topology cannot get it anymore? Like you will start losing tweets or messages or whatever you're consuming. How to overcome that problem? Burst in traffic. That's what we did. We introduced queuing layer. We use Kafka for that. What is Kafka? Apache Kafka, it's open source, I would say, messaging system, right? It's fast because it saves everything to local hard drive. It's scalable. It's distributed. Well, it's durable because it's always save messages to local disk. And it's distributed system. It's partitioned, and it could be distributed among machines. So it's indeed scalable. And it's worked very well with Storm. Probably 90% of people who use Storm use it with Kafka, not with other like message queue system. You can, but Kafka is the best fit, right? So what we did, we introduced that messaging system. So now if we have burst in traffic, suddenly it will be saved in Kafka, and as our Storm will pick it up. Of course, it will introduce latency, but you will not lose anything. So depending, if it's constant, permanent, like traffic increase, you increase your topology. If it's like happened once in a blue moon, at least you save. And that's bring you to like generic blueprint of streaming processing. So you have streaming source, you have message queue, and then you have Storm or any other streaming processing. And we like this so much because, as you see, it was quite easy. And we use it for a lot of different things. So we have topology that does real-time indexing for Solr. So before our document from content system end up in Solr, we have to do some XML parsing, cleaning, some business logic, whatever. So we use, again, we generate as editor hit submit button. It just go to Kafka, process, stream processed, and end up in Solr index. What's about all this messages, all these documents that we have in database? Sometimes you have to reindex the whole collection of documents. And we use Storm for batch processing as well. And the idea is quite simple. We use Spring Batch, I believe. We just get all data from database and flat files, send it to Kafka, and use the same logic, practically the same code, to run it as a batch. So we have both words, streaming, real-time, and batch process. And it's end up in Solr. Well, also we have interesting things. I said one of a use case when, let's say, doctor reading article, we want to display advertisement that match to what he's reading, for example, or any other business rule. So we create a rule engine in Groovy, using Groovy DSL, where our business folks, they create using that specific DSL, practically they say, if doctor and his specialty is cardiologist reading the article with this subject, assign him marketing campaign and such. And that's, they write in a DSL, which is translated to Groovy script. And we run that thing inside Bolt, right? So we listen to all click streams. So when he click on that article, that he's viewing this article, the whole thing get executed, marketing campaign saved to database, again, MongoDB in our case, and other applications that like ad server or email servers, they're responsible for displaying that. They pick it signal and display it. So Storm allows us to do it so real time with very low latency. Otherwise, it doesn't make sense. He's gone from the site, right? And it's scale. So if we have 100 rules, we just put more resources. Yeah, here's our DSL. And let's say you've done all this job and you want to tune your storm topology. And that's what we did. So what's happening, sometimes people telling us that tweet get lost. Somebody tweeted and it didn't end up in our application. How you know that the whole pipeline is still running? You don't, right? Maybe nobody tweeted at this time. How you know, right? So what we did, we create a synthetic monitoring. So we have create a robot, that simple script that tweets. He tweets every, let's say, 2 minutes, right? And on the receiving end, we get tweets that he's tweeting, and we check. If it didn't come, it means it's failed. So we have put it in Xenos and alerting operation starts that something wrong, right? So that's like called synthetic monitoring, which allow you to see if everything is okay with your topology and actually with any web service, right? Also, when you do Storm deployment, it's very useful to have Graphite, and Storm comes with metrics API that allow you not only put like performance metric, but also business metrics. So you can graph them easily and see what's going on with your topology. And there's a nice article, and I probably don't see it, but Michael Knoll wrote about how to integrate Storm with Graphite. For those of you who's not familiar, how to install Graphite and what it's all about. But there's libraries that do that. And when you're talking about optimization, you know, Storm processes a lot of data, so everything may count. So you have to optimize that execute method. You don't care about everything else. Just execute method, make sure it's fast as possible. And for example, a lot of people calling some web API to get the same JSON all the time. What we did, we use Google Guava caching library, which are very useful. So instead of calling it 100 times and get the same response, we just cache it. And Guava cache has provision to how to invalidate cache, because when you start caching, the most important problem when you invalidate. So Guava can say invalidate in 10 minutes, or invalidate first in, first out, this type of stuff, right? And if you use Groovy, compile static helps to make it faster. If you do need such a difference, it's maybe very small, but again, it's there. And these are resources available nowadays. There's like 4 books, actually, yeah, 4 books dedicated to Storm and Big Data book and a lot of material on internet. But those books are really good. And one Big Data book written by Nathan Mart, who created Storm, and he's talking about Lambda architecture, how you combine Storm and Hadoop to create a robust big data architecture. And that's very interesting. And this one, Storm Blueprint, it's mostly about like real use cases, and they use Trident for each example. Very interesting read as well. And a demo for this will be available on my GitHub repositories. And I guess that's all I have for today. And if you guys have questions, please. Yes? No, I don't. I just learned. The only thing I know, Storm is a like 2-year-old project, very mature, and Spring it just released a couple months ago. Yeah, beyond that, I don't know much about Spring XD to make comparison. Yes. Yes. Redis versus Kafka? Yeah. Well, you can use Redis. There's no doubt about that. Kafka has some ability to replay from the same, to support like this transactional topology in Trident. Kafka has this notion because all data about consumers stored in Zookeeper. So Kafka doesn't know who's connecting and do what, you see. So that's maybe the difference.
And also with Redis, I mean, the cluster was only showing up now. Yeah.
We didn't. We just saw that looks like Kafka has all semantics to support Trident and to support Storm. And we had very outdated in our corporation message system, JMS something. I think it was JMS based. So we say, let's do Kafka. Yeah, please. Trident? Trident, it's not a separate project. It's part of Storm. So when you, it's like a, yeah, it's part of Storm. When you install Storm, Trident, of course, available right away. And what's happening when you write your Trident function, it will convert it to Storm, Bolt, and Spouts.
And is there any relationship between Spring products and Storm or Trident?
Spring products?
Yeah, like Spring. Is there a Spring Storm?
No, not. For now, not. Nothing, yeah. I did integration with Spring, but it was done on a Bolt level when I instantiate Spring context and you reuse all the Spring dependency management inside Bolt. You can do that.
You do it yourself?
Yes, it's, yeah. Yes.
It seems to me that often in real-time applications, the concept of time duration is really important. Like we really want to know, like, over the course of history, how many times has this word been used, but how many times in the last hour has this word been used? And I always feel like that's when this gets really complicated. Like when you break it down so that your time buckets are small enough that you have that window that says it's the last hour and says the number of counts. Does Storm have anything to help with that type of a problem?
You mean, okay, the question, if I understood right, how to write something that's saying, let's say, how many times something happens in 1 hour or 2 hours. Yeah, actually, yes, in Trident and in real plain Storm, you can do that. And what we did like most popular article in last 10 minutes, right? Or most popular, that's what's original use of Storm was. Most popular tweet, like trending topic. It's called trending topics, for example, for tweets, or trending, whatever trending. Yes, that's the use case for Storm. And it's published, actually, in that book about Trident, how to do it. And also on the internet, this article, how to do trending topic in Storm. Yes, that's what it's about, real-time analytics, and that's one of the part. Yes?
Are there any security concerns about this? Let's say you want to put it over the internet and just have those servers communicate with each other.
Right now there is no server, you have a cluster, of course you have to open so they communicate to each other, at least at some ports. There is support for each GVM, so you have to open those ports. But there is no built-in security, like even for admin interface, even for this UI, there is nothing. And that's where Storm direction is, adding security, and vendors as well, community working on that as well. Yes. Any other questions? Okay, thank you for coming. Enjoy your stay.